Hello, chemistry students, and hooray, this is the very last section in Unit 6. We're going to look at nuclear chemistry today. Just to introduce this, the protons and neutrons that are bound together within an atomic nucleus are bound with much, much greater forces than those that bind atoms together to form molecules. So you can see why the nucleus is actually a very attractive source of energy. In fact, energies associated with nuclear processes are more than 1,000,000 times those associated with chemical reactions, the energies in those nuclear reactions. So we're going to look at two types of nuclear reactions, fusion and fission, and critical mass, chain reactions, nuclear reactors. Those are some of the things that we will address in this section. So let's first look at fission versus fusion. You probably already learned this. Fission is splitting a heavy nucleus into two nuclei that have the two nuclei then would have smaller mass numbers. And then fusion would be, Fusion would be just the opposite of that. We would take two light nuclei and combine them to form a heavy nucleus. So let's take a little bit of a look at each of these processes more in depth. We're going to see that they can supply amazing quantities of energy with relatively little masses of materials. So let's look at fission. Nuclear fission was discovered in the late 1930s when uranium-235 nuclides were bombarded with neutrons and observed to split into these two lighter elements, as well as releasing 3 neutrons and lots of energy. In fact, for every single mole of uranium-235 that undergoes this reaction, 2.1 times 10 to the 13th joules of energy are produced. When we compare that to the combustion of methane, 1 mole of uranium-235 undergoing this reaction produces 26 million times as much energy as 1 mole of methane being burned. So it's a tremendous amount of energy. So as you can see, this particular process of fission is only one of actually many different fission reactions that can occur with uranium-235. Also, a lot of different isotopes for a lot of different elements have been observed undergoing nuclear fission. In fact, 35 different elements have been observed undergoing nuclear fission, 200 different isotopes out of those 35 elements. And here we have written down critical mass. What is that? You've probably heard that word. Before we can talk about what critical mass is, we need to look at what a chain reaction is. So in addition to the product nuclides here, neutrons are also produced in all of the fission reactions of uranium-235. In this one, 3 neutrons are produced. As those neutrons fly through that uranium sample, they may collide with other uranium-235 nuclei, producing additional fission events. Right here you have that happening. And each of those fission events produces more neutrons. And those neutrons can in turn produce more fission events of the uranium-235 nuclei. So because each of the fission events produces neutrons, this process can be self-sustaining. At least 1 neutron from each fission event must go on to split another nucleus, however. So if on average less than 1 neutron causes another fission event, then the process will die out. But if exactly 1 neutron from each fission event causes another fission event, that process sustains itself at the same level, and it's said to be critical. So if more than 1 neutron from each fission event causes another fission event, This process rapidly escalates, and the heat buildup causes a violent explosion. So one can see the big difference between this process being critical and getting out of control and out of hand. And hopefully you can see the two applications, right? If we have a situation where the process is critical, and we have exactly one neutron from each fission event causing another fission event, then we can use that for useful energy. When it rapidly escalates out of control, you can see the application, of course, being a bomb. And that is exactly what the United States carried out in the Manhattan Project, was research on the principles of nuclear fission. That program is what introduced the fission bomb and was used in 1995 in devastating acts on Japan. And basically, that fission bomb operated by suddenly combining subcritical masses, which I'm going to explain in just a second here, and that resulted in those rapidly escalating fission events. Critical mass, that is what we were looking at before. What is critical mass? It is simply the amount needed to achieve the critical state. So this is an important number, because if the mass is too small, too many of the neutrons will end up escaping before they have a chance to cause a fission event, and the process dies out and stops and never occurs. So because of the tremendous energy involved, fission has been developed as an energy source to produce electricity. We have reactors here where controlled fission can occur, and the resulting energy from that is used to heat water. This is water that's being heated, producing steam here that ends up running turbine generators in much the same way that a coal-burning power plant generates energy by heating water to produce steam. This right here represents the water, the cooling water that is usually derived from a lake or a river that is used to condense the steam after it leaves the turbine. So if we take a closer look at the nuclear reactor core, we can see how scientists have figured out how to make this work. It's really interesting. Basically, in the core, uranium is enriched. Natural uranium doesn't contain very much uranium-235. It only contains about 0.7%. So the uranium is enriched so that it's about 3% uranium-235. They found that percentage works best for these reactions. And then it is housed in metal cylinders. This would be the uranium here, where it is. The moderator surrounding the cylinders here, it's a graphite core. The job of the moderator is to slow the neutrons down so that the uranium fuel can capture them more efficiently. Control rods here, those are composed usually of like cadmium, and they absorb the neutrons, and they are used to regulate the power level of the reactor overall. The reactor is designed so that if a malfunction occurs, the control rods are automatically inserted into the core so that they can absorb neutrons and stop the reaction to prevent a catastrophe. We usually have liquid, usually it's water, the coolants, that is circulated through the core. We have the cold coolant coming in, the hot coolant leaving, and that is to basically absorb that heat generated by the energy of this fission reaction. Also, the heat leaving then would be used to run the turbines, and in turn generate electrical energy. So that is what the schematic of a nuclear reactor core is like. You can see that it's really important that it be built to prevent any accidents, right? Because you've all heard of 3 Mile Island or Chernobyl in the Soviet Union in the late 80s, where there were meltdowns. Meltdowns occur when the cooling system fails to any degree, really, and then that can lead to temperatures high enough to melt the reactor core. So obviously, there's a huge danger to nuclear energy. So that is one of those great debates in science and in politics, whether or not to continue building fission-based power plants. So now let's turn our attention to nuclear fusion, the process of combining 2 light nuclei. That produces even more energy per mole than fission. In fact, stars produce their energy through nuclear fusion. Our sun presently consists of 73% hydrogen, 26% helium, and 1% other elements. It gives off vast quantities of energy from the process of nuclear fusion, fusing protons together to form helium. We don't know exactly how this works. One possible scheme for this process is just shown right here in these reactions. This just stands for neutrinos. We're not really looking at those right now, but again, it is sort of a series of events that ultimately leads to the formation of helium nuclides and a lot of energy. So because of the tremendous amount of energy released in nuclear fusion reactions, obviously scientists are trying to think of a feasible way to capture that energy. The fusion process, though, is a lot more difficult to initiate than fission. This is because the forces that bind the nucleons together are only effective at very, very, very short, small distances. So in order to bind protons together, they have to get extremely, extremely close together. And protons obviously are identically charged. They obviously repel each other. So in order for 2 protons to get close enough to bind, they have to be shot at each other at speeds that are extremely high, so that speed, the velocity, will overcome their repulsion for each other. And those repulsive forces are so great that we have to basically raise the temperature to 40 million Kelvin in order to get the velocities high enough to overcome that repulsion between the protons. And that is kind of difficult to do. Right now, 2 types of processes are being looked at in order to try to achieve those extremely high temperatures. High-powered lasers are one, heating by electric currents is another, and so maybe one of you will look into nuclear chemistry in your life and overcome this interesting problem that we're facing. So main points here: fission versus fusion. Obviously know the difference, know what a chain reaction and critical mass are, know how a nuclear reactor works, basically, for the most part. Here's some advanced ideas. Also, another advanced idea: what is a breeder reactor? What problem are they seeking to solve, and what is it that they do in their function? So I look forward to seeing you in class and seeing what you have and what questions you might have. Have a good rest of your day.